How's it going, guys? Today we're going to be going over 7.4, day 2, dividing polynomials using synthetic division and also some applications of synthetic division. So first thing I want to look at is just look at this box right here in the top, and we have two partitions in this box, right? We have the long division part and the synthetic substitution box. In both parts, we're doing the same process. We're dividing 3x cubed plus 4x squared plus 0x plus 10 by x minus 2. But we're going about it in two different ways. On the left side, under long division, that looks pretty long, complicated, and it's a lot of work. You guys remember from the last video, if you did a few problems yourself, it can be pretty tedious, it can be pretty long. On the synthetic substitution side, you can see that it looks pretty short, quick, and easy to do. It's very clean. And that's the pro of using synthetic substitution, is that when you can do it, it's much quicker, much faster, and much more efficient than using long division. But there is a caveat with that. When it comes to synthetic substitution, you can only use synthetic substitution when you're dividing by x minus a, or when your divisor is x minus a. All right? So that means we can have stuff in the form x plus 3, x minus 3, x plus 7, whatever it is. These parts over here, they're okay. But if we had something like, say, 2x plus 7, or x squared minus 8, or, I don't know, 3x minus 9, none of these would work. Over here, none of these would work because the x has to have a coefficient of 1 and a degree of 1. It cannot be raised to any power. It cannot have a coefficient other than 1. The a can change as long as the a is an integer, any type of real natural number, it's okay. So that just means like any whole number or any number in general, it works as long as it doesn't have a variable with it. Let's put it that way. All right, the a can be any number as long as it's a real, number without a variable. But the x cannot have any coefficient other than 1, and it can't have a degree other than 1 as well. All right, so let's go ahead and do a problem. An example, on number 1, we have 4x cubed minus 6x plus 9 divided by x plus 3. So here we can see that our a is going to be negative 3, right? Since it has to be in the form x minus a, x plus 3 is the same thing as writing x minus negative 3. So you can see our a is negative 3. And once we have our a value, what we're going to do is we're going to take it, and where we plan on doing our synthetic substitution problem, we're going to put it in the top left corner. So you put our a there, and after we put down our a, we need to write down our coefficients of the dividend. And if you guys remember from the last video, we put placeholders with long division, right? If we go back up to the box over here, we see that they put the 0x as a placeholder for long division. And we're going to do the same thing with synthetic substitution, but the only difference is with synthetic substitution is that you have to do it or you're not going to get the problem right. With long division, you can get away with not doing it. It makes it a little harder to follow, and it makes it easier to make mistakes. But with synthetic substitution, you have to do it or you're not going to get the problem right. Okay? So for number 1, we see we have a 4x cubed. The coefficient of that is 4. After 4x cubed should come the square term. We don't have a square term in this polynomial, so that means we're going to put a 0. After the square term comes the degree of 1. That's going to be negative 6. And lastly, it's going to be 9. After that, we draw a line a little bit underneath the row of coefficients. And now we're going to actually do our synthetic substitution. That's how you set it up, and now we're going to solve it. All right? And to solve it, what we do, we bring down the first term underneath the line. So when we bring it down, we can put a 4 underneath the line, and once we do that, we're going to multiply whatever's underneath the line by our a value. In this problem, our a is negative 3, so we're going to do 4 times negative 3, that's negative 12. And once we do that, we add going down. So we multiply by our a going up diagonally, and we add going down. So 0 plus negative 12 is negative 12. And then we're going to multiply by our a going diagonally. Negative 3 times negative 12 is a positive 36. Okay? And then we're going to add going down. Negative 6 plus 36 is a positive 30. and then we're going to multiply going back up. 30 times negative 3 is negative 90. Okay? So anytime you put a number underneath the line, you have to multiply it by a to put it back above the line diagonally. Okay? So that's what we're doing, and then we're adding going down. And then lastly, we have 9 plus negative 90 is negative 81. And this last term right here, that's going to be your remainder. Okay? So we have our remainder, and we have our quotient right here. All this right here is called our Q of X, or our quotients. Okay? And how we write this down as our answer is that we take this first term, and that's going to be 1 degree lower than the number we're dividing by, or the number we're dividing. So in this case, we have 4x cubed. That's the third degree. So this 4 right here, that's going to be in the second degree. So we get 4x squared, and we just go down degrees from here. 4x squared minus 12x plus 30 plus, we write our remainder like we did in the last video, negative 81 divided by our divisor of x plus 3. So negative 81 divided by x plus 3. And this right here will be your solution to number 1. Okay? So let's go ahead and do number 2 as well. For number 2, we have 2x cubed plus 5x squared minus x plus 7, all divided by x minus 2. So with x minus 2, we can see that our a is going to be 2. It's in the form x minus a already. So our a value is this right here, our 2. So you put our 2 in the top left corner. We're going to write out our coefficients. We can see that our dividend, we're not missing any terms. So we don't have to worry about any zeros. So we'll just put 2, 5, negative 1, and 7. We'll draw our line, and we can start solving. The very first thing we always do is drop down the first term. All right, we always have to drop it down. We're not multiplying it to put it down. Just add it down to 0, we drop it down, and we have a 2. And then from here, we multiply with our a to go back above the line. 2 times 2 is 4. And then we add back down. 5 plus 4 is 9. Then we multiply with our a to go back above the line. 2 times 9 is 18. And then we add down. Negative 1 plus 18 is 17. Then we multiply with our a to go back above the line. 2 times 17 is 34. And 34 plus 7 is 41. And we don't have any more terms to multiply or add with, so we stop here, and our last term is our remainder. So let's go ahead and write down our solution. And we can see that our dividend right here, the first term is in the third degree. So our 2 down here is going to start with the second degree. So you have 2x squared plus 9x plus 17 plus our remainder of 41 divided by our divisor of x minus 2. And this right here will be our solution to number 2. All right, for number 3 and number 4, I want you guys to actually pause the video, take about 6-7 minutes, however long you need, to actually solve it out. And then I'll put the answer and the worked out solution in a few seconds, okay? So I'll give you guys a little bit to pause the video. Okay, so here's number 3 and number 4. That's the worked out solutions. If you got something different than I did, look at what you did and kind of compare with what I did and see what you did differently. Okay, I think the biggest things people might mistake here or make mistakes with are going to be the zeros of the placeholders. Number 3 here, our dividend right here for number 3, it goes from the 4th degree to the 3rd degree, all the way to the 1st degree. We're missing the 2nd degree. So that's why you put the 0 over here. It has to go from the 4th to the 3rd to the 2nd and then to the 1st. So you have to put in a 0 or you're going to get the answer wrong. And same thing with number 4. We go from the 4th all the way to the 2nd degree, where you kind of jumped over the 3rd degree. You can't do that when it comes to synthetic substitution. So you have to put in the 0 as in our synthetic substitution. All right? So that's usually the biggest thing I saw with these 2 problems. Your people are forgetting to put in the zeros for the placeholders. You have to put them, or you're going to get the problem wrong. Okay? So let's keep on going. We're going to talk about the factor and remainder theorem. The factor and remainder theorem, they sound a lot worse than they actually are. So for the factor theorem, all it's saying is that if you're doing synthetic substitution and you get a remainder of 0, then that x minus a that you're dividing with is a factor of the polynomial. Okay? So if you're dividing, if you're using synthetic substitution and you get a remainder of 0, that divisor that you're using is going to be a factor of the polynomial that you just divided with. Okay? And then for the remainder theorem, if you have a polynomial p of x and it's divided by x minus a, then the remainder is p of a. So that's just saying if you're using synthetic substitution, whatever your remainder is the same thing as just putting your a value into the problem itself. So if you want to go back one slide to number 3, our remainder here when we had an a value of -1/3 is 7, right? We had a remainder of 7. That 7, we look on the same 7 if we took this -1/3 and just plugged it into here. If you plugged in our -1/3 into our polynomial, we would have gotten 7 as well. That's what the remainder theorem is saying. And you're going to see why it's useful when we eventually use some problems directly for the remainder theorem. So let's do a problem or two for the factor theorem. For the factor theorem, we have x cubed plus 3x squared minus 4x minus 12, and we're dividing all of that with x plus 3. So we're going to set up our synthetic substitution, because remember, the way to tell if x plus 3 is a factor of that polynomial is if we get a remainder of 0 when we do our synthetic substitution or even long division. Okay? But synthetic substitution will be much easier. So let's set it up. We can see that our a value here is -3, since it has to be in the term x minus a. So our a is -3. We're going to set it up. We're going to put in our coefficients. We're not missing any terms, so we can just write it all out. 1, 3, -4, and -12. We're going to drop down our first term of 1. -3 times 1 is -3. 3 plus -3 is 0. 0 times our a to go back above the line is 0. We add down. -4 plus 0 is -4. We multiply with our a to go back above the line. -3 times -4 is a positive 12. And then we add back down. -12 plus 12 is 0. So we see that we have a remainder of 0. So that means that x plus 3 is going to be a factor of our polynomial, since x plus 3 divided into our polynomial perfectly. We don't have a remainder. It divides into it perfectly. It's a factor of that polynomial. So what we're going to do now, because we actually are asked to find out the completely factored form of this polynomial, is that we're going to take that x plus 3. We're going to take our divisor. We're going to bring it down over here. And we're going to multiply it with our quotient right here. Right? We said our quotient is our terms right here. We're going to multiply our divisor with that quotient. So with 1, 0, -4, we see our x to the third in our polynomial is in the third degree. So our 1 is going to be 1 degree less than that. So we get x squared plus 0x minus 4. Okay? And from here, what we're going to do is we're going to see if we can factor this out anymore. So x plus 3. And we're just going to rewrite this without the 0x since it's redundant. And we can see here that x squared minus 4 is in the form, it's in the factoring form of the difference of two squares, right? If you don't remember the difference of two squares is, it's saying we have a squared minus b squared. That's the same thing as a minus b times a plus b. It's in the same form. Our a is x, our b is 2. So we can rewrite this as x plus 3 times x minus 2 times x plus 2. And this will be our completely factored form for number 1. Okay? So that's how you do it. If you want a formula that goes along with the factor theorem, it's going to be if your remainder is 0, our factor is going to be x minus a times our q of x. Okay? So if you want a formula, that's what it's going to be. If you get a remainder of 0, the factor will be x minus a multiplied by the quotient that you got from your synthetic substitution. And then you have to see if the q of x can factor out any more from there. Okay? So let's go on to number 2. So we need to see if x plus 1 is actually a factor of x cubed minus x minus 24 or not. So we're going to do our synthetic substitution. Our a is -1. We'll put in our coefficients. For x cubed, it's a coefficient of 1. We don't have an x squared term, and we cannot go from the 3rd degree to the 1st, so we have to put in a 0. After that, we have -1 and -24. We put in our line, and the first thing we always do is drop down the first term. -1 times 1 is -1. 0 plus -1 is -1. -1 times -1 is 1. -1 plus 1 is 0. 0 times -1 is 0. And 0 plus -24 is -24. So we don't have a remainder of 0, right? -24 isn't 0, obviously. So that means that x plus 1 is not going to be a factor of x cubed minus x minus 24. So we can just write not a factor for this problem here. For number 3 and number 4, I'll let you guys do it on your own. We do post a completed key on Canvas. You can double check your work there if you want to. I highly encourage that you do. It's good to get as much practice as possible. But for now, we're going to go on to doing the remainder theorem. All right? So for the remainder theorem, what we do, right before we start talking about the remainder theorem, let's actually just do number 1 first. For number 1, we're being asked to find p of 2 the old way by substituting, right? If you remember, guys, we want to find the value of p, the function p, at a value of 2. That's just a fancy way of saying x equals 2, plug it into the function. So x equals 2, we're going to plug it in. So we have 2 times 2 to the 4th minus 3 times 2 to the 3rd plus 4 times 2 squared minus 5 times 2 plus 1. All we did was plug in 2 into our function. Next, we're going to solve this out. 2 to the 4th is 16. 16 times 2 is 32. 2 cubed is 8. 8 times 3 is 24. 2 squared is 4. 4 times 4 is 16. -5 times 2 is -10. And we have that plus 1 at the end. 32, -24, and 16. All that gives us is 24. 32 minus 24 is 8. 8 plus 16 is 24. So we cross all that out. Then we have minus 10 plus 1. 24 minus 10 is 14. And 14 plus 1 is 15. So p of 2 in this problem here gives us 15. And now we're going to actually try to solve this using the remainder theorem. Okay? So like I said before, the remainder theorem, what it means, or what it is that if you're doing synthetic substitution and you have an a value and you do something, your remainder using the synthetic substitution is the same thing as plugging in your a into the equation, and you get the same exact thing. So it still sounds a little confusing to hear. So let's actually just see what I mean. So we're going to put our x value here as our a value, and we're going to put in our coefficients of the p of x. So we have 2, -3, 4, -5, and 1. We're using our p of x in the problem number 1. Okay? So we're going to do synthetic substitution. We're going to drop down to 2. 2 times 2 is 4. -3 plus 4 is 1. 2 times 1 is 2. 4 plus 2 is 6. 6 times 2 is 12. -5 plus 12 is 7. 7 times 2 is 14. And 14 plus 1 is 15. So our remainder is the exact same thing as problem 1. Okay, so that's what the remainder theorem is saying. Maybe it makes a little more sense now when I word it out. It's just that when you do synthetic substitution, whatever you get as your remainder is the same thing as taking your a value that you used with synthetic substitution and plugging it into the equation. And it can be really helpful when we have problems like number 3, right? For number 3, we see we're asked to find p of 5. If you start trying to find 5 to the 3rd power plus 3 times 5 to the 2nd power, and so on and so forth. It's going to be very big numbers. It's going to take us a bit, but it'll be much, much quicker when we're doing synthetic substitution, right? It helps a lot when you have bigger and uglier numbers to deal with. So that's kind of the perk of the remainder theorem. All right. Same thing. I'm going to leave number 3 and number 4 for you guys to do on your own. Other than that, guys, that's pretty much the whole video. I don't want this video to drag on for too long. Hopefully this helped, guys. And, do the example problems I left for you guys to do and double check your work with the completed key on Canvas.